I'm going to teach you about diffusion. Okay, this is the first part of diffusion. Recall we're talking about transport across the membrane. All right, so diffusion. This is passive transport across the membranes. The part we are talking about. Recall we have active transport across the membrane. We also have passive transport across the membrane. So david7stancytheater@gmail.com. You can contact us and consult. Right. So David 7 Science Theater, a good channel to watch. We have a couple of videos, very many videos about science. You just watch. Don't forget to subscribe to our videos. You like our videos? They are good, yeah. You click the bell for notifications every day we upload videos. Comment and share. Comment, we shall see the comments below. We're going to go a little further. There's a lot to discuss today about diffusion. It is a lot, but we shall finish this video in the next few minutes, probably 20 or 15 minutes. We shall be done. And diffusion refers to passive transport of molecules from areas of higher concentration to areas of lower concentration. It is passive. It should be occurring along the concentration gradient from higher to lower concentration. Even osmosis is diffusion, okay? Because we're having water moving from a region of its high concentration to a region of lower concentration, okay? By that is diffusion of a solvent. All right, that is osmosis. So diffusion can be simple or facilitated diffusion. When is it simple? It's simple because we have transport of atoms or molecules occurring from one place to another due to just their random movement. They are moving randomly, okay? And the molecules, as they are doing that, they do collide due to constant rapid movement. Due to constant movement, these molecules collide with each other and also strike the cell membrane. And this occurs at a frequency which will be higher on the side of the membrane, having higher concentration of a particular molecule. If molecules are too much outside the membrane, the frequency of collision and striking the membrane will be higher. Okay, and this process there will occur a net flux of molecules from areas of higher concentration to areas of low concentration, either going out or getting into the cell. And that is with respect to the cell. But if it is just a membrane separated by fluids, separating fluids, it means movement from a higher concentration region to a region of lower concentration of that very or particular molecule. And the net movement of the molecules ceases when the concentration of molecules equals, okay? And at this point we call it a diffusion equilibrium. When we have the same concentration of those molecules outside or inside the cell or at either sides of the membrane. So there's this man who quantitatively classified this diffusion, the simple diffusion, by his law. And it states that the rate of diffusion is directly proportional to the difference in the concentration of the substance, which you can call concentration gradient. Therefore, it is directly proportional to concentration gradient, that is, you can call it C1 minus C2, and cross-section area, yes, that is A, and also inversely proportional to the distance to be traveled, and that is what we call the thickness of the membrane. So we can simplify it as here. The rate of diffusion J is direct proportional to the distance, is direct proportional to the diffusion coefficient, direct proportional to the area across which diffusion is occurring, and also to the concentration gradient, and inversely proportional to the thickness of the membrane. So this is the diffusion coefficient. It's not the distance. The distance to be traveled, we call it the thickness of the membrane. Lipid-soluble substances. How does simple diffusion for lipid-soluble substances occur? Recall we have lipid-soluble substances and we have substances which are not going to dissolve in the lipid on the phospholipid bilayer. So what will happen for lipid-soluble substances? The rate of diffusion through the lipid layer will be directly proportional to the solubility of those substances in the lipids. Okay? If it is highly soluble, the faster or the higher the rate of diffusion. If it is partially soluble, so if it is partially soluble, it means it will have lower rate of diffusion. Therefore, molecules of substances like oxygen, nitrogen, these are mentioning the lipid-soluble substances. So they are molecules of oxygen, molecules of gases like nitrogen, carbon dioxide, molecules of alcohol, molecules of steroid hormones, and weak organic acids or bases. These are lipid-soluble and they will diffuse very rapidly through the lipid bilayer of the cell membrane. Alright, so water and other lipid-insoluble substances. Water does not dissolve in lipids, that is right. And we also have other lipid-insoluble substances. How will they cross the membrane? Lipid-insoluble substances and water can also pass easily through the membrane. But how is this possible? It is possible due to the presence of the so-called protein channels. These are made from the transmembrane channels. Transmembrane proteins are proteins which are traversing the phospholipid bilayer. From ECF to ICF, the protein touches either sides. Okay, so these channels are made from those transmembrane proteins, and these transmembrane proteins are existing within the cell membrane. For example, just as you can see this, have transmembrane proteins which are making a channel. This channel which can transmit water can also allow other lipid-insoluble substances to go through it. The protein channels are tube-shaped channels from extracellular matrix to intracellular ends, and they are characterized by their selective permeability. They are selectively permeable, and 2, they have a gating mechanism. So we are going to talk more about simple diffusion in that direction. We have gating mechanism, we're going to talk about that. We're also going to talk about the selective permeability of the protein channels. We're still talking about simple diffusion. We haven't switched to facilitated diffusion. Alright, so the protein channels are highly selective, i.e., each channel can permit only one type of ion to pass through it. And this results from the characteristics of the channel itself, such as its diameter, its shape, its nature, nature of electrical charges along its inside surfaces. So these are good determinants of what will be transmitted, what will be carried, what will be channeled through that protein. Okay, and the examples of some selective channels, we know we have sodium channels. These are strongly negatively charged within the interior surfaces, okay, and they can only transmit a molecule of 0.3 by 0.5 they are 0.3 by 0.5 nanometers in size. Okay, so sodium can only be transmitted through sodium channels. So is potassium. Potassium is only transmitted through potassium channels, and 0.3 by 0.3 nanometers. Okay, so these are not negatively charged. The potassium channels are not negatively charged. So we're switching now to the gating mechanism of the protein channels. How is the gating mechanism occurring? Some protein channels are continuously open, that is right, whereas most other channels are gated. And to say gated, they are equipped with actual gate-like extensions of the transport protein molecule, which can open or close as per as the requirement is. So if we need to open it, it will open. There is a gate-like extension which exists on the transport protein. So this gating mechanism is a means of controlling the permeability of the channels. The opening or closing of the gates are controlled by 3 major principal pathways, where we have voltage, we have ligands, which you can say this is a ligand-gated channel, this is a voltage-gated channel. We also have mechanical gated channels. So those are the 3 important mechanisms you can note out of how these channels are gated. So if we are talking about voltage gated channels, You can see here we have two channels. We have sodium gated channels on the right, on your left. We also have, but we have on the right, yeah. We have sodium gated channels on the right. Sodium ion channel here. You can see it is strongly negatively charged, while the potassium channel is not negatively charged. Okay, so the sodium channel is strongly negatively charged, as you can see. When it is voltage gated. Okay, this one is also voltage gated ion channel, the potassium channel. And another thing to note here is that the sodium channel is more responsive. It responds faster than the potassium channel. In case you see the inside of the cell, the intracellular fluid, if the membrane is negatively charged on the inside, okay, the sodium channel will be closed. The gate will be closed if the membrane is strongly negative inside. But as that negativity reduces, where like in nerves, as we saw, as that negativity reduces, the sodium ion channel gets opened faster, and the opening increases faster. But for the potassium channel, even after reducing the negative charge inside to turn to positive, the potassium channel opens slowly. Okay, you can't note it here, but you should know it. So let's continue. The gated mechanisms are basically three. We have voltage gated, ion channels, or channels, and these respond to electrical potential. For the ligand gated channels, these respond to chemical binding, while mechanical gated channels will respond to mechanical stretch. So the voltage gated channels, they will respond to electrical potential across the membrane. For example, we have potassium channels and sodium channels, which are where the potassium channels will show slower response than sodium channels, reducing negativity inside the membrane. And the ligand-gated channels will open when other chemical molecule binds with the gate protein, such as acetylcholine effect on the postsynaptic membrane channels. Alright. The mechanical gated channels will open during when there is mechanical stretch. And these mechanosensitive channels play an important role in cell movements. Also know another case where I have mechanical gated channels, for example in the ear. Yeah, in the ear, you have heard me. The cochlea. When we have transducing in the transduction of the sound waves within the cochlea, within the organ of Corti, is it? Yes. When we are transducing sound waves in the organ of Corti, the hair sensory cells, that is, it means I'm magnifying it a little further. Organ of Corti, hair sensory cells now. Each hair has a mechanically gated channel, and that channel permits potassium and calcium to enter the hair. Okay, and finally the cell. Okay, so that hair has a mechanically gated potassium channel up there. You know that we shall talk more about it. Let's continue. Facilitated diffusion is now we're going to right now. So the water-soluble substances having larger molecules, such as glucose, cannot diffuse through the protein channels by simple diffusion. But otherwise, such substances will diffuse through the cell membrane with the help of some carrier proteins. Therefore, this is what we call carrier-mediated diffusion. So the water, when it is dissolved larger molecules like glucose or amino acids, it will not be able to pass through the protein channels. We've seen those are also selective for size and for charge, so shape, yes. So these ones will go through the protein carriers or carrier proteins And glucose and most of the amino acids are good examples carried by the specific carriers in facilitated diffusion. And the mechanism of facilitated diffusion is simple. The molecule to be transported will bind the site on the carrier protein in the extracellular fluid. We shall have binding of the molecule amino acid of glucose on the binding site of the carrier protein, and this binding will cause conformation changes within the protein channel or the carrier protein. And these conformation changes, this does not use energy. They are just conformation changes which are not dependent on energy, so it is passive. These conformation changes will find that molecules are released from the binding site when the conformation change occurs. So there is something like flipping here, such that the binding site is now facing the inside or the interior of the cell, interior of the membrane, the intracellular fluid, as we call it. So the conformation change has happened. The site was in the extracellular fluid, it's now in the intracellular fluid, hence releasing the molecule from the binding site. Types of carrier proteins. There are basically three types. As you can see here, we have an import carrier, we have a symport carrier. You see the arrows are showing import, ECF going to ICF, which is a single molecule. Then we have a symport carrier, we are having both molecules entering into the cell. Then we have an antiport carrier, where one is entering and another one is getting out of the cell. So, according to the arrows we have here, we have three types of carrier protein systems: uniport, symport, and antiport. Talk more about that. Antiport carrier protein transports only one type of the molecule, and the symport carrier will transport one substance. Like let me talk it in this way: that a symport carrier, there is transport of one substance which is linked to the transfer of another substance. For example, facilitated diffusion of glucose in the renal tubules is linked with the transport of sodium. So to reabsorb glucose within the kidney nephron, we are using sodium first, then we are carrying it with the glucose. That is a symport transport system. For the antiport transport system, the carrier proteins exchange one substance for another. For example, we shall be having sodium potassium exchange or sodium proton exchange in the renal tubules. So the three transport systems are existing with carrier proteins. So you should recall that these are passive, they are not utilizing energy. Okay, so you should differentiate it from having secondary active transport, symport, or antiport carriers. Okay, so this is just facilitated diffusion, where one type of molecule is conjugated with transport of another type of molecule. So I just urge you not to forget to subscribe to our videos. That is the end of this video. Click the bell for more videos. We upload it daily. Like our videos. I know they are good. Comment and share. Thank you.